kiddos, today we're going to talk about part 2 of the classification of matter. We're going to talk about mixtures. In the previous video we talked about pure substances, which were elements and compounds, one type of particle, and we talked about how to split those things apart and be able to tell some things about those. In tonight's video we're going to talk about mixtures, which means we're going to talk about things in which there is more than one type of particle in whatever sample of the substance that you're looking at. And so what that means for us is that in the case of mixtures, there is a spectrum of mixtures. A lot of times we like to make things out as though they're like these really clearly defined categories, and we can categorize stuff certainly. But really there's a spectrum, there's like a gradation of different types of mixtures. And so the simplest way to split those apart is to talk about homogeneous and heterogeneous mixtures. And those words mean essentially what you think they do, in that homogeneous means that the mixture is the same throughout. In fact, what we would normally say about that, like the subscript that I would normally give to that to students when they think about that, is that it has a uniform composition. Okay, and don't let the word composition there throw you off. It just means that it's the same all the way throughout, that if you took a sample of it at any one point and then took a sample at another point of that it's all going to be the exact same thing. So my favorite example is that of sweet tea. So in sweet tea you've got water, okay, so you've got a solvent, that's the water, and then dissolved into that solvent you have a bunch of solutes, and we'll talk about those definitions a little bit when we talk about solutions in particular. So you've got sugar dissolved in it, and then you've got all of the chemicals that were in the tea that you were steeping in it. So you've got tannins and caffeine and all those other sorts of things dissolved in it. But when you look at that glass of sweet tea, assuming that everything's been put together properly, the sweet tea is the same at the top of the cup as it is at the bottom of the cup. Everything is completely homogeneous throughout. Okay, on the other end of the spectrum, we have heterogeneous mixtures, which means that they're non-uniform, that they're, for lack of a better term, sometimes maybe chunky, that you can see particles in them. The example I always like to use for that is that of vegetable soup. So vegetable soup, you've got broth, okay, so that's sort of your solvent, but then within that you've got a bunch of vegetables and maybe some noodles, and you got carrots and potatoes and tomatoes and green beans and all of those sorts of things. And so you might take a spoonful of it, and in one spoonful you get 2 pieces of potato and some broth, and the next spoonful you get a green bean and a carrot and a potato. And so it's heterogeneous. It's not the same throughout. That if you sampled it in different parts, you would get different amounts of stuff. And so that homogeneous and heterogeneous, we can then sort of further split down into 3 separate categories, which is how we're usually going to define our mixtures. And those 3 separate categories are solutions, okay? At the other end of the spectrum, we have suspensions. Okay, not from school. It means that something is suspended in the solvent. And then in the middle here, we have something that we call colloids. Okay, so we got solutions, colloids, and suspensions. And they sort of work in this continuum here. Solutions are always and forever pretty much completely homogeneous. Suspensions are heterogeneous, and what that means is that like either we can very clearly tell things apart, or in many cases if we let it settle for a little bit of time, stuff would start to fall out of it. And so a good example of a suspension is if we went out to the good old Tennessee River out there and you scooped out some nice muddy water, some of that nice orange water, and let it sit for a couple of hours, the particles that are suspended in that's why we call it a suspension, the particles that are in the water are slowly going to settle out of it. And that is sort of characteristic of suspensions, is that things will settle out of them. Solution stuff is pretty much never going to come out of it. Colloids are sort of there in the middle, in that stuff can separate sometimes, but things really shouldn't totally fall out of that. Okay, and so let's talk a little bit about then why, why is a solution different than a suspension and a colloid, aside from like just the definitional thing, like what chemistry-wise makes them different from one another. So what really matters here with the mixtures, like in terms of matter, like what actually makes them different from one another, is the size of the particle that is in the solvent. The solvent, again, is the stuff that the thing is being dissolved in. So in a lot of cases for us, water is what we're then mixing something in. It certainly doesn't have to be water. There are thousands of other solvents. But water is sort of the most ubiquitous, the most common solvent that we have for things. So when I said my example earlier of taking some dirty or muddy water out of the river or out of a lake. So water is the solvent. That's the matrix. That's the thing that the other stuff is in. The other stuff, of course, is like particles of dirt and rocks and clay and that sorts of things. And so those are the particles that are suspended in it, or if we were in a solution, we would call them the solute. So those suspended particles, what makes a suspension different than a solution is the size of those suspended particles. So if you look at all three of my particle diagrams here, the little Mickey Mouse looking things there are, those are water molecules, okay, oxygen, 2 hydrogens. And then in each of those, you'll see I've sort of drawn out, like, not really to scale, but just to give you an idea of how that works, of what the different sizes are. So the particles in suspensions are these really big particles. You can probably see those with your naked eye. You could just look in the mixture and be able to say, oh, there are particles in that, like there's some dirt in there. If you poured some water and there was visibly dirt in it, that would be a suspension, and you shouldn't drink that water, okay? In a colloid, the particles are smaller, and so they're probably not going to settle out the same way they would in a suspension. They would sort of stay floating within the solvent matrix, but they're definitely a lot smaller than suspensions. So we've gone from a factor of anywhere greater than 1,000 nanometers, okay, and so that goes up to about a micrometer, and much bigger. So I mean, it could be rocks, right? I mean, it could be something that's 4 centimeters across, could be part of the suspension. Colloids, we're talking about pretty small things. So we're talking about like from a nanometer scale up to almost a micrometer scale. So things like maybe fat molecules. So a good example of a colloid is something like milk, where milk is mostly water, and then you've got some other things within that mixture. So you have some of those things that are dissolved like they would be in a solution, things like lactose, the sugar that's in milk. And then at the same time, you would have things like fat molecules that are like these really big molecules that are like 200, 300 atoms big sometimes. And so those molecules are pretty big, and so they're not able to dissolve completely in the same way that say, maybe the sugar molecules in the milk would, that would be the solution part. Instead, we've got this colloidal mixture of the fats there that are in that. Now, does milk settle out? Not really. I mean, if you've got milk in your fridge, I mean, it's probably going to stay in there even if you left it past the due date. It's going to stay, that way it's going to stay there for probably a couple of weeks or a month or something like that. Part of the reason is because your milk has been homogenized, which basically means that it's been spun really rapidly to mix everything up so that everything's emulsified and stays together. But if you set that out on the counter and gave, say, some of those fats and stuff and proteins sometimes to coagulate and all of that stuff, then things would start to separate out of there in the way that they wouldn't really in the case of a solution. The sugars that would be dissolved in it are not going to come out of the solution unless you actually get rid of the solvent. So what about solutions? Well, in solutions, the particles are really small. So I've got these really small dots. You'll notice there's 2 different ones. So I was essentially saying if you dissolved a salt in there, and so you'd have sodium and chloride ions. Or again, you could dissolve something like sugar in there, which is, even though sugar is a relatively big molecule and that it's got, about 40-something atoms in it, it's still relatively small when we compare it to a fat molecule that has a couple of hundred atoms in it. And so those smaller particles essentially get completely surrounded by the particles of the solvent, the water in our case, and so they sort of keep it wrapped around almost in like these little cages, and it holds them there, and they don't just come out of the solution. And they're really, really tiny. You wouldn't be able to see them. What about in the other two? Well, in the suspension, we said you would definitely be able to see them. In a colloid, you could kind of see them. And what does that mean? Well, colloids tend to be like very, at best, translucent, and at worst, often very opaque, or they might appear very foggy. Fog actually is a really good example of a colloid. It's a colloidal suspension, essentially, of water droplets suspended in the air. That's what fog is, and so that's a colloid, where you've got some sort of big particles of water where they've condensed together and they're suspended in the air. That is a colloid. And so things are going to look foggy, and that leads us to something else about colloids. One of the things that you'll often be asked to do is to tell the difference between them. So to tell the difference between them, suspensions will settle out. In other words, if you left them out for a little bit of time, the particles are going to fall out of the container or fall down to the bottom of the container. In the case of colloids, things aren't really going to settle out given normal circumstances, but colloids exhibit what we call the Tyndall Effect. And what the Tyndall Effect means is that if you shine light through them, that they look really foggy. And so again, fog is a great example of that. Fog already looks foggy, you say, but if you shine your lights of your car through that fog, you can really sort of see almost the individual particles of it. And that's what you can do in the colloid. That's sort of how you can see the particles in it. If you had a liquid colloid, you could do the same sort of thing. If you shined a light through it and you could sort of see individual particles in it, those would be the big solute particles in the colloid that you would be able to see. In a solution, you could shine a light through it and it would go straight through, and you wouldn't be able to see any of the particles that are within it. If you shine that through sweet tea, you're not going to be able to see the sugar particles. You're not going to be able to see the caffeine particles. You're not going to be able to see all the tannins and stuff like that are dissolved in there. And so that's what solutions are going to look like. Okay, so that's a pretty common thing to have to be able to tell between the mixtures. So there are two schemes there that you can go under mixtures. You can do the broad schemes where you say, hey, it's homogeneous. Everything looks the same when I look at it. It's heterogeneous. It looks visibly different when I look at it. Or you can break it down into somewhat smaller areas of suspensions, colloids, and solutions. Remember that this is a spectrum, that there's like a sliding scale here. So is there a hard cutoff that, hey, at 2 nanometers, it's now a colloid? No. At 100 nanometers, it's definitely suspension. No, I mean, this is a, sort of a fuzzy gray area. Sometimes things can be somewhere in that gray area between colloid and suspension. Sometimes things can be a little bit in that area between solutions and colloids. But most of the time, you can make a pretty clear guess as to which is which. It settles out. It's definitely suspension. Does it look foggy? We're going to call that a colloid. Can I not see anything even when I shine a light through it? That is a solution. Okay? And so that's mixtures in a nutshell. We're going to dive into a lot more this year, in particular solutions, because a lot of what we do in chemistry is we're going to take things that are dissolved completely into a solution where we can't really see the particles anymore, but the particles are there, and we're going to use those particles to do some effects and do some chemistry on. Okay, so that's mixtures. And real quick, I want to sort of do a quick breakdown on particles and go back to the diagram that we had in the last mixture thing. So let me put that up real quick and we'll run through that. Okay, so real quick, let me run through what I think is a nice, easy little dichotomous key to help you identify the things, to break down matter and be able to classify it. So here we go. If it's one type of particle, then we go into the pure substance category. Within the pure substance category, if there's one type of atom in it, then it's an element. If there's more than one type of atom in it, it's a compound. Okay? So that's the pure substance branch. If it's more than one type of particle within whatever you're looking at, then it's a mixture. If that mixture is uniform, if you look at it and it looks the same all the way throughout, then that's a homogeneous mixture. And then if that homogeneous mixture is clear, okay, or at least transparent, then that is a solution. If that homogeneous mixture is sort of foggy, cloudy, or opaque, then that is a colloid. If that mixture is not uniform, then that is a heterogeneous mixture, and we would classify that as a suspension. Of course, knowing that there's not really a real quick, clear split between these, that there's a little bit of a spectrum. But that gives you a nice, sort of quick way to sort of run through something in your brain and say, okay, is it a pure substance? Is it a mixture? Is it homogeneous, heterogeneous, element, compound, whatever? That's your classification scheme that you need to know for the classification of matter. All right? Thanks, kiddos.